about OpenMP for Python.
Thank you. So I'm Dorian. I did that project as part of my studies in HPC in the University of Santiago de Compostela. And nowadays I'm a programmer for XWiki on totally unrelated project. So the topic of today is implementing OpenMP for Python. So it's a new library called OpenMPY. I'm going to talk about another library as well that does the same thing. So in Python we have a built-in threading library that's called threading. That introduces a thread class and functions together a bunch of things about threads and their other threads, the current threads and other threads that are currently running. It introduces the concept of local memory for threads. We have features of synchronizations, but we had for a long time the problem of having a single thread being able to run at a given moment. I'm sure many of you are aware of the GIL. I'm going to come back to that. Okay, yes, sure. I'll speak up. So there are some use cases for using threading, despite that limitation, which is parallelizing input-output, maybe having a GUI where you can have an event-based system. And also, you can still run parallelized code using threading by releasing the GIL in functions implemented in other languages. So we already have some implementations of OpenMP in Python that are PyOMP and Python. Maybe more exist, but those are the ones I came across. So PyOMP is an extension of Numba, and it compiles the Python code on the fly to an LLVM intermediate representation, and then to machine code. But again, this comes with limitations because we can't run any code written in Python. It's not transparent. You need to use supported libraries by Numba. You need to re-implement libraries that are implemented in other languages for them to be compatible. Python is another solution that has built-in support for OpenMP. However, it's highly limited in its support of Python itself because we can't create classes. We can't create classes in Python. So we're limited to, I think, my understanding of the project was prototyping for mathematical usage mainly. We have ways of parallelizing code in Python, for instance, multiprocessing, running different processes, different instances of the Python interpreter, and transferring data using inter-process communication. There is the library concurrent.futures, which wraps threading and multiprocessing as independent implementations of the same concept. And I can mention async.io, which is an event-based approach similar to what you can have in JavaScript to have a multi-threading. Not multi-threading, to have a parallelization of tasks and input-output. So recently, Sam Gross, an engineer at Meta, a year ago, I think, opened PEP 703 and worked on a fork of Python to remove the global interpreter lock and make threading in Python actually useful for improving the performance of programs. So he started with a fork in 3.9 and rebased it in 3.12 and merged it in 3.13. So the PEP 703 defines that removal of the GIL. It was implemented in 3.13, as I said, which was released recently in October 2024. So you need to compile Python with a specific option, which is disable GIL. And at runtime, you need to also specify that you are running without the GIL, because that removal of the GIL has impacts on existing programs. If you're going to run a library that wasn't, a program that wasn't thought with the GIL in mind, you're going to run into concurrency issues that you didn't have without the GIL, with the GIL, sorry. Because there is more concurrency than before. The GIL is a global interpreter lock. So when removing it, some instructions, you could consider them atomic despite the fact that you're using threads, and existing libraries already use threads in Python, and those will break when removing the GIL. So there is a lot of work to do to make Python support that removal of the GIL. So I'm introducing a library that's called OMP. You can find it on PyP, on the Python package index. Not under the name of OMP, unfortunately. This one was removed because of AI hallucinating and researchers thinking it's a great idea to claim the name. So that library implements, the name for the library on the Python package index is OpenMPy, if you're looking for it. I'll show the links later. So the library implements the OpenMP API. I'm going to go over the different directives supported. It's a usage that's similar to OpenMP in C, but taking into account the specificities of Python. And one of the requirements that we had in that project was to use only Python standard libraries, so the library doesn't have any dependency. For the usage of the library, once imported, you can call the OpenMP class with the directive as a string parameter. For simple directives. And for constructs, you can use that same class as a context manager. And we also implement the primitives simply under the OMP namespace. So I'm going to show some example of code so that you can have an idea of what it looks like. Okay. So here I'm importing the library OMP. I need to decorate my main function with omp.enable, and what that does is it's going to read the source code of that function and do a sort of pre-processing for it to do the correct translation of the OMP directives, of the OpenMP directives, so that it's doing the threading and managing the variables. So in that example, it's a pretty simple one. I'm just summing the numbers from 1 to number n that is defined here. That's big so that we can see the performance. Yeah. So I'm using a reduction and the schedule parameter is the schedule parameter is something that's important to tweak for performance, especially in Python, and that's a big difference that we'll see with the usage of OpenMP you can have in C, because you need to take into account the base performance of Python. So this is a native Python implementation of OpenMP. So we're still going at the pace of Python. We're not going faster. We're just parallelizing what's happening. So that's the usage of the library. When removing the decorator OpenMP.enable, the code runs seamlessly as if we didn't have the OpenMP directives. Those don't do anything when the decorator is not present. So on the performance, here I tried running that code with different chunk sizes. And what we can see is that we do have a speed up. So that's great news. But it's not great. So here you have the time on a log scale, and here the number of threads. I was able to run my code on a supercomputer node at Finisterre 3 in Galicia, in Sesga. So thanks to them. I don't have access to that computer anymore, so I can't run more advanced examples. But I'm sure you have many ideas of usage for that library that fits your purpose. So about the chunk size, what's interesting is that there is a sweet spot where we gain some time. So we're using dynamic scheduling, and Python's syntax is tricky to manage because this is a for loop, and so this is an iterator. And the way I implemented that library is that it works for any iterator here, not only range. So far, the dynamic scheduling is going to unpack that iterator and distribute it to the different threads as we're going. So when running with a short body, like this one that's only doing one operation, it's going to be, we're going to lose time simply unpacking the range itself. And unpacking the range takes most of the time compared to simply updating the accumulator. So I have another example where I defined a function, a very simple one that checks if a number is prime. So it's meant as a heavier computation than just adding a number to an accumulator, since I have to call prime first on bigger and bigger numbers. So here we can see the difference again in runtime, depending on the number of threads. And we achieve a much better speed up, which I think showcases the time we lose unpacking the range. So there are some optimizations that can be done to that unpacking by specifically having an implementation for the ranges, and still fall back to that unpacking distribution for other iterators. Yeah, it uses multi-threading under the hood, nothing fancy here. But we do have to manage variable scopes. So the nice thing about, So the nice thing about that library, compared to other techniques of multi-threading, is you don't have to care much about the variable scope. It's exactly like in OpenMP, so that accumulator, I can access it here, I can access it outside of the thread when I print my result. Outside of the threads, yeah. So there's that. On the supported directives from OpenMP, not all of them, we have parallel with a private clause. We have a for with no aid, private reduction and schedule. We have parallel for with no aid, private reduction and schedule as well. We have a barrier directive. We have a critical. We have single. And that's it. So that's the support that's currently implemented. I'm interested if you have ideas of usage or how it could be useful to you and what could be missing in that library. And yeah, that's it.
Questions for Dorian? Yeah.
Yeah, all right. There are a number of clauses you call OpenMP with. In this string, you have for, you have, what else? Yeah, you have a number of clauses. Are there documentation regarding what these clauses do?
Repeat the question.
Yes. So the question is there a documentation for what the clauses do? So we're just following the OpenMP specification here. Is this still muted? No, it's not.
It's not random.
It's blinking.
Maybe the battery.
Okay. Yeah. Let me find it. I have it here. Yeah. So you can read the OpenMP API, and you have the explanation of what the clauses do. I'm just following this. I did do some modification for the for directive for the scheduling. I changed the default. I switched it to dynamic because of how the fact that I don't have a specific range implementation affects the performance. So I decided that dynamic was a better default.
All right, so it's completely mimics the C API then?
Yes, other than that you need to call OpenMP.
Yeah.
Yes, another question?
Yep.
Go ahead. Yeah.
The scale, the chart of performance that you showed, it looks like it doesn't scale beyond 6 cores or something?
So it depends on the task. Yes, sorry. Good point. So about the runtime that I showed, it seems that it doesn't scale above 6 cores. Where did we have that? Here? Yes. Maybe I'll put that document online so you can access it on the presentation page. So yes, it depends on the kind of task. On that task specifically, yes, we do reach a minimum pretty quickly, where adding more cores doesn't bring any benefit, and that's because of the unpacking of the range. So what I get from that is we really need to have an implementation specifically for the range and not unpacking the range as any iterator and distributing the elements.
So you think like if you have a different workload, you could scale to 60 cores?
So the question is, with a different workload, could I scale to 60 cores? The answer is yes. Here is a different workload, and you can see here that we keep gaining time. And I do have the speed up chart here, so that talks more maybe. So for 64 cores, we're at about a speed up of 50. So that's a heavier task. It's a different one. We do achieve a speed up. We are able to compute different things at the same time.
More questions?
Go ahead.
Ooh, many. Okay.
So at some point it reads the iterator to distribute them across threads. What happens if the iterator is taken, for example, generator?
So the question is, given that we read the iterator elements and distribute them across threads, what happens if the iterator is infinite? Pretty much the same thing as if you weren't using OpenMP. So you have an infinite iterator, your for loop is going to run infinitely. That's it. Other questions?
How does it compare with processing? How does it compare with the wiki processing package of Python?
So the question is, how does it compare to multiprocessing? The library multiprocessing. That's an interesting question. The goal of that library is purely syntax trigger. It's not about making multi-threading performance better in Python. So I didn't do a comparison of the performance with multi-threading. I think it's more of something that's interesting in the work that Sandros has been leading of removing the meal itself. So sorry I can't answer it more precisely.
One more question? Yeah.
You're working clearly on this lovely report, but this report is, can you put it in the slides or make it available online?
I didn't understand the question. Can you repeat it?
Well, you're showing a report.
Yes, I'm going to put it online. Sorry, I did not.
Yeah, let's wrap up here because we have to change the battery for the night. Thanks so much.